Go. Hello and welcome back to Statistics1. I almost said calculus. Oops. We are finishing up chapter 7. We are going to take a look at the sampling distribution of the sampling mean, not sampling mean, or sample mean. Oh, I just have this title wrong. This is what happens when I grade all day and then there you go. Sample mean. Perfect. Sample mean. Nice. So what we know so far here in purple, we know that mean of means is equal to the mean, and we know that standard deviation of sample mean is the population standard deviation divided by the square root of n. So now we take a look at the normal distribution, right? And normally distributed variable x. So let's write the sampling distribution of the sample mean for normally distributed variable. So suppose that a variable x of a population is normally distributed. You are immediately thinking heights, shoe size, IQ, all that stuff. With mean, mu, and standard deviation, sigma. Then the samples of size n the variable x bar is also normally distributed. And has a mean of mu and standard deviation of sigma divided by square root of n. So what this does is it pushes further this idea that eventually we can take a sample and infer what population mean and standard deviation are. Because in the future, we want to look 100% at the sample and do not depend on any of the population parameters. So if your variable x, which can be shoe sizes, IQs, and whatever else, if your variable x for all people on the planet, or the sizes of all tarantulas on the planet, as we had the problem before, if these all are normally distributed, that the samples of those variables would also be normally distributed. And that's important to us because we want to have the same distribution, and then we want to use the sample to predict and infer what the population is going to be. Now, one of the most important theorems in the entire stats universe is the central limit theorem, right? And it technically says that for a relatively large sample size, right? And that relatively large sample size would be n larger than 30. So you're looking for 31 and above. Your project sample size is supposed to be, I said 90 to 100, 120, 150 data points, because we don't want to have the very small sample. You know that for elections, they poll over 100,000 people. You say, wow, that's a lot. 100,000 people is a lot. Yeah, but compare that to actually 350 million, right? I mean, not everyone votes, but let's say 200 million, right, are over 18. I really don't know. But let's say it's 200 million over 18 and voting, then 100,000 in comparison to 200 million is nothing, right? But it's a large sample size, and it's a good sample size. And if it's diverse sample size, meaning non-biased one, you didn't go to, just New York and, went into 3 city blocks and collected those, but you actually did it in all parts of the country and, reached people in different ways, then, yeah, you can have a good prediction of which way the election would go. So let's take a look at the central limit theorem. Known as CLT. For relatively large sample size, I'll just put n larger than 30 in parentheses. The variable x bar is approximately normally distributed. Regardless of the distribution of the variable under consideration. Regardless of the distribution of the variable under consideration. The approximation becomes better with a larger sample size. Now, just to draw some of these out. So this is going to be population, n equals 2, n equals 10, n equals 30. Now it's going to be tricky to draw, but so we have a bell-shaped curve, and then it remains bell-shaped curve as you go through samples. So this is your variable x, and all of these are x bars. So this is nothing surprising. If you already have the normally distributed variable, then the sample means will also be normally distributed. That was a theorem before, central limit theorem, and it was no surprise. But then, if you have reversed J distribution on your x, it is interesting to see what happens with x bars. So this becomes right skewed, and then you have almost bell-shaped curve, and then you have a bell-shaped curve for n equals 30. This is why we are looking for 30, sample size 30 or bigger. If you have the uniform, right, the flat distribution on x, then for x bar equals to 2, you have one of those triangular, and then it becomes normal distribution as you have more samples. So now I hope you see that, n equals 30, all three of these are normally distributed, which means we can use our mean of means and standard deviation and all of that stuff. We don't have any new formulas or anything. It is just this idea that if your sample size is larger than 30, the sample means are normally distributed, and you can do these calculations. Now in chapter 8, we're going to go backwards and then actually use this. All right, so teacher salaries, loan amounts, nurses. What should we take a look? Poverty, early onset dementia, worker fatigue. What should we look at? Worker fatigue. All right, so there is a study in American Industrial Hygiene Association, volume 64, pages 352 to 359, if anyone wants to look it up. Assessed fatigue in steel plant workers due to heart stress. If the mean post-work heart rate for casting workers equals to, this problem is 777. So if the mean of worker equals the normal resting heart rate of 72, so our mean mu is 72 beats per minute, that's the BPM unit. Find the probability that a random sample of 29 casting workers will have mean post-work heart rate exceeding 78, so mean larger than 78.3 BPM. Assume that the population standard deviation is given as 11.2. BPM. State any assumptions that you are making in solving this problem. Great. So they want us to find the probability, right? So what do we have? We have the mean and we have the standard deviation. They want us to figure out what is the probability to have a larger than 78. Well, in order for us to do any of those probabilities, hence use the z-score chart and all of that good stuff, we need to have normally distributed variable, and since n is 29, that's almost like 30, right? So we'll call that 30, 31. If that was 15, obviously this would not hold. Or if it was about 29, 30, 31, that's all in there. So we know that from here I can compute that mu x bar is equal to 72, right? And from here I'm calculating that sigma x bar is equal to sigma divided by square root of 29. Well, let me put n first. N. And sigma was given as 11.2 divided by square root of 29. So we can find sigma x bar when you punch these things in the calculator. So we have 11.2 divided by the square root of 29, 2.08. This is also BPM and BPM. So now these are our parameters that we will be using to calculate. So now our distribution, which is now normal distribution, in the middle is going to have 72, and then 1, 2, 3 standard deviations on each side. And you can add 2.08, right? Because this is the distribution of x bar variable. This is not the distribution of. So you can compute now the z-score. And if you compute the z-score, you would use the z-score of 78.3 minus 72 divided by 2.08. So this is going to be 6.3 divided by 2.08. And that's going to equal 2 point something, right? 6.3 divided by 2.08. Oh, it's 3.01. 3.01. So now z-score of 3.01. Now, guys, that's all the way here, right? That's where the z-score of 301 on a z-scale, because on a z-scale 72 is where the 0 is. So now they're asking for the probability larger than 78.3. Well, we calculate the area to the left because that's what the z-score chart gives us, and then subtract from 1. So the z-score for 3.01 is 9987. So area is 0.9987, which means that area to the right is 1 minus 0.9987, which is equal to 0.0013. So what's the percentage of people? What is the percent of what is the probability that the randomly picked worker will have the resting heart rate larger than 78.3? Probability is 0.13%. It's extremely small probability to have this. So same calculations, except now instead of using your mu and your sigma, you're using mu x bar and sigma x bar to calculate z. Once you have z, we do want area to the right, which is this very tiny area to the right of the red line. But to get to that area, since the chart gives us the area to the left, you calculate area to the left first, and then you subtract that from 1, because the entire area under the curve is equal to 1, which is 100%, and then you subtract the area to the left. Yes?
So when you say mu is greater than 78.3, is that supposed to be mu x bar?
Yes, thank you very much. Mu x bar. Yes. So they want... No, sorry. This is not mu. This is supposed to be x, right? Great. Then casting on a man. Oh no, you're right. All right, good. So no new formulas. We're just putting all these new concepts together on one spot and setting up the stage for chapter 8, which is going to be the most powerful chapter that we find here. Yes?
So there are two mu x bars for the 72 and 78.3?
They want to see if what is the probability to find the sample of sample size 29 so that the bar is so that the mean is so that the mean is not 72, that the mean is 78.3. Let me jump back to answer your question. Let me jump back to 7.1 where we have an example over here where we talked about, I think, Bill Gates and all of these rich guys, right? And we said that their mean is 46.5, right? But if you take a look at the 46.5 billion, which is the mean of the population, right? I have that the mean of all means, which is mean x bar, is going to be the same number, right? But look at this mean. It's 65.5. So technically we are asking what is the probability that if you are to pick at random 2 is going to be those two that gives us 65, right? That give us a different mean. Because we also want to know how likely it is for us to be wrong, right? That's another thing that we worry about as we do statistics. Sounds good? All right. So let's go in chapter 8 and do some really cool stuff.